Hello everyone, and welcome back. Today we're going to be introducing a very beautiful topic known as partial differential equations, which has so many applications in the real world in practically every single field in existence. So, to start, what exactly is a partial differential equation? So, practically all of ordinary differential equations involves a function of one variable only. So what a partial differential equation and also systems of partial differential equations discusses and explores are equations of more than one variable in one or more functions together with all or some of its partial derivatives with respect to those variables. So, is it possible that we can solve some partial differential equations even though we haven't really talked about any unique methods in order to solve them? Of course, yes. So let's start off with a couple very basic trivial examples of partial differential equations, sometimes called PDEs. So let's begin by letting u be a function of both x and t. All right, so two variables. Let's assume one spatial, x, and one temporal variable, t. So what we're going to do is solve ut is equal to u. So what is the general solution to this PDE? So let's just write it out in expanded form. So what we have is the partial derivative with respect to time of uxy is equal to uxy. So what I want to do is sort of treat this like we did for separable differential equations in the single variable world. And I can just write this as the partial differential of uxy. And that's going to be divided by uxy. Actually, instead of y, I want to actually write this as t. Let's just stay consistent. So uxt, 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 uxt. And that's going to be equal to the partial differential of t. And then I can integrate both sides of this equation. And then I'm just going to have the natural log of uxt on the left-hand side. And that's going to be equal to t plus some constant with respect to time, in particular a function of x. So let's sort of explore why this is the case, just in case you're not too sure. So this is true because the partial derivative with respect to time of a constant of x only is equal to 0. So in some sense you can view that the null space of the partial time operator is the set 0 and the set of all functions containing x only, right? So since it doesn't have t, it's a constant as far as t is concerned, right? So c1x is practically the null space of the time partial derivative operator. So once you have that, then we can solve this equation for u. So once we exponentiate, we're going to have uxt will be equal to e to the t times e to the c1x, but e to the c1x is still just a function of x only, so what I can do is say, okay, uxt is going to be equal to c of x times e to the t, and that is the general solution for the partial differential equation ut equals u. So let's solve another PDE that looks almost the same as this first example, but a little different. Let's solve ux is equal to u. So if we solve ux equal to u, again, that's just the same thing as the partial derivative with respect to x of uxt, and that's going to be equal to uxt. And we can isolate our differentials, so we're going to have the partial of uxt all over uxt would be equal to the partial of x, and then we can integrate both sides of this equation. And then we're going to have the natural log of uxt, and that's going to be equal to x plus some constant. So what is the null space of the partial x operator? Well, we know that's just going to be the set of all functions 0 and also any functions of t only. So that means we're going to have some function of t, let's call it c1 of t, and then we can exponentiate and redefine our constants. So we have that the general solution to this PDE is just going to be equal to some function of t times e to the x. right? So we obviously can solve some very trivial PDEs where we only have one partial derivative, either x or t, of a multivariable function, let's say u of x and t. But PDEs are actually a little bit more interesting and a little bit more practical when you have two or more partial derivatives in the same exact equation, and especially if you have them of higher order. So for example, let's assume that we have ut plus ux is equal to 0. Right? So this is a partial differential equation because, again, we're going to be assuming that u is a function of x and t only. Here, we have the partial derivative with respect to time of u, and then we have u times the partial derivative with respect to x of u, and that's going to be equal to 0. So what we have here is a first order time derivative, a first order spatial derivative multiplied by u. So what we have here is a nonlinear term, right? So this equation might be super complicated to solve, but notice that this equation is homogeneous, so that might be allowing us to solve it, in some easier way. But this particular PDE is actually a special case of a more general PDE. So it's a special case of the equation ut plus ux is equal to nu uxx. So when we talk about PDEs in a little bit more of a physical context, we're going to be calling this a diffusion term. And in terms of the applications of this equation, sometimes this is called Burger's equation. Burger's equation. It has a lot of physical applications in the realm of fluid mechanics, and this new term is sometimes called the viscosity coefficient. So if we want this Burger's equation to sort of reduce to the equation that we started with, in particular this homogeneous PDE, we want that viscosity coefficient to be equal to 0. So this particular equation is sometimes referred to as the inviscid Burger's equation. So the inviscid Burger's equation is just a homogeneous Burger's equation where the viscosity coefficient is equal to 0. So what I'm going to do is I'm going to propose that the solution to the inviscid Burger's equation is of the form f of x minus u of t. Right? So I'm going to claim that this is a solution to this PDE. Right? So it's actually a class of functions. It's not like sine or cosine or e to the x. It's more so just horizontal transport functions of some arbitrary function f. And depending on my initial condition, something called the boundary condition of this PDE, you can figure out what type of function f actually is. Right? So what I want to do is verify that this actually is a solution to the PDE. So how to verify? So the first thing that I want to do is I want to differentiate this function with respect to time. So the partial derivative with respect to time of this function, f of x minus u of t, what is this going to be? And you may want to pause this video to sort of see if you can find it on your own. So this is going to be equal to, so by the chain rule, f prime, so the derivative of the outside of x minus u of t, times the partial derivative with respect to t of that interior function. In this case, it's going to be x minus u of t. So keep in mind, x is a variable, t is a variable, and u is a function of both x and t. So as far as t is concerned, x is just a constant. So the partial derivative with respect to t of x is just 0. So what we're going to have is the derivative of the outside, again, times, and then we're going to have that minus 1 sort of chilling in the front. And then we need to do some product rule in that term. So it's going to be equal to u times the derivative of t with respect to t, which is 1. And then plus t times the derivative of u with respect to t. So I'm going to write that as ut times t, or you could write it as t times the partial u of t. Let's write it like that. So t u of t. So that is the partial derivative of t with respect to this claimed solution. Let's do the same for x. So the partial derivative with respect to x of x minus u of t. So by the chain rule, again, we have f prime of x minus u of t times the partial derivative with respect to x of that interior function again. Again, x is a variable, t is a variable, u is a function of both x and t, but t is a constant as far as x is concerned. So what we're going to have is f prime of x minus u of t times the derivative of x with respect to x is going to be 1, and the derivative of u with respect to x is going to be equal to ux, and we can write that as minus, we can write that as tu of x. Right? So that gives us that particular term. Now what I want to do is I want to plug these two things in into our differential equation, which is again ut plus ux. And we're going to see, is this really equal to 0? So what we need to do is substitute these two partial derivatives into the left-hand side of this equation together with the assumption that u is equal to f, and show that that linear, or in some sense nonlinear combination, is actually equal to 0. So once we do so, what will we get? So we're going to have, so let's start with this term. So we're going to have f prime of x minus ut times minus 1 times u plus t ut. And then we're going to have plus u, which is fx minus ut, times our partial derivative with respect to x, which is f prime of x minus ut times 1 minus t ux. Right? So that gives us this expression. And actually, let's keep in mind that that is actually just u in disguise. So what I want to do is I want to distribute this term into the first and second very carefully. So many things can go wrong here. So we're going to have minus u times f prime of x minus u of t. And then we're going to have minus t ut times f prime of x minus u of t. So that's the first expression. And then once we distribute this into that bracket, we're going to have plus u f prime, keep in mind that's just u, f prime of x minus u of t, and then we're going to have minus u times f prime of x minus u of t times t u of x. So let's sort of take a step back and see what we have here. Notice that we have a minus u f prime and a positive u f prime. So they're going to cancel each other out, so that's actually quite nice. And then we're going to be left with two terms that both have a negative sign in front. So I can factor out that negative sign. So we're going to have negative 1 times what? So we're going to have t ut times f prime of x minus u of t. And then we're going to have minus u, or let's write it as f prime of x minus u of t times t u ux. Right? So what else do we have here? So we have a t in common. We have a f prime in common. So let's just factor those out since they're in common, right? So we're going to have minus 1 times t times f prime of x minus u of t. What we're going to be left with is ut minus u uxx. Oh, and that minus should have been a plus because we factored that sign out. So ut plus u ux, and that's what we have. But keep in mind, we're assuming that this u is a solution to this particular equation, so that means it must satisfy ut plus ux is equal to 0. But keep in mind, we don't want to sort of enter a circular logical argument here. But keep in mind, nowhere in this expression of ut plus ux are we assuming that u is actually equal to that particular function, right? Because this equation, by definition, is equal to 0 for any solution u, even if we don't necessarily know our f is a solution. Alright, so that means this expression is precisely equal to 0, and 0 times whatever this function has to be must be equal to identically 0 as well. So since what we got when we plugged in our little transport function f is that it comes out to 0. And that means that is indeed a solution to this Inviscid-Burgers equation, in particular a solution to this PDE. Now what I want to do is I want to classify some very commonly studied partial differential equations, in particular of second order. So to make this simple, we're going to assume that these PDEs are constant coefficient, but technically they could be functions as long as they are well behaved. But let's just assume that they are constant coefficient PDEs just for the sake of simplicity, at least for today. So what we're going to do is we're going to, again, assume that u is a function of x and t only. So one can verify, at least in some process of elimination, or maybe from a conic section perspective, that every second order constant coefficient linear PDE can be represented in the form a uxx plus b uxt plus c utt plus d ux plus e ut plus f u equals g. And obviously if g is equal to 0, then we would call this PDE a homogeneous PDE. So there are three main categories that are usually studied in detail in the realm of second order PDEs. The first is where b squared minus 4ac is equal to 0. So if b squared minus 4c is equal to 0, then we call this PDE a parabolic PDE. And another case, if b squared minus 4ac is less than 0, we call this PDE an elliptic PDE. And 3, if b squared minus 4ac is positive, then if you remember anything about your conic sections, we will call this a, take a guess, a hyperbolic PDE. Right? So parabolic, elliptic, and hyperbolic partial differential equations. So let's look at a couple of PDEs and see if you can classify them as parabolic, elliptic, or hyperbolic. So example 1. Let's assume that we have ut is equal to uxx. This is a very famous equation. This is often referred to as the heat equation. So what is this? So the first thing that I want to do is I want to rearrange this and write it as uxx minus ut is equal to 0. So what we have here is that a is equal to 1. We have that e, keep in mind e is the coefficient of the ut term, so we have that e is equal to minus 1, and then b, c, d, f, and g are all equal to 0. So if we do b squared minus 4ac, what will we get? So b squared is equal to 0 minus 4a and c, which is equal to 0. So that's just 0 minus 0, which is equal to 0. So if the discriminant, let's say, is equal to 0 for this PDE, then this is a parabolic PDE. Right? So the heat equation is an example of a parabolic partial differential equation. Let's look at another example. So example 2. Suppose we have uxx plus utt is equal to 0. So it's already in what we call standard form, so we can easily identify the coefficients. So we have in this case that a and c are both equal to 1, and b, d, e, f, and g are all equal to 0. So that means b squared minus 4ac is equal to 0 minus 4ac. So that's going to be equal to minus 4, which is negative. So if the discriminant of the PDE is negative, then we say that this equation is an elliptic PDE. And this equation has a name. This is called the Laplace, or Laplace's equation, right? And it should look familiar, at least from multi-calc, because this is practically the Laplacian operator of u. Sometimes people will write it as so. And let's look at another example, another famous PDE. Let's look at UTT is equal to UXX. This is often called the wave equation. The wave equation. So let's first write this PDE in standard form. So that's going to be equal to UXX minus UTT is equal to 0. And what do we have here? So we have A is equal to 1, C is equal to minus 1, B, D, E, F, and G all equal to 0. So that means B squared minus 4AC, which is 0 minus 4, 1 minus 1. This is going to be equal to 4, which is greater than 0. That means the wave equation is an example of a hyperbolic PDE. Now, we're not going to get into the details of what is the difference between the solutions of parabolic, elliptic, and hyperbolic PDE, but I just want to give you the heads up. These are three main categories that you definitely could spend a lot of time talking about for each of these categories. Practically sort of how we have the homogeneous and the inhomogeneous, the linear, the nonlinear, the first order, the second order, and so on. But the behavior, generally speaking, for these categories are usually very different. Now that we've discussed just a couple basics about PDEs, for example, how to verify solutions or PDEs, some basic classifications of common second order linear constant coefficient PDEs, now let's actually go through an example of how to solve a very important PDE. In this case, we have ut is equal to alpha uxx, which is again the heat equation, which is an example of a parabolic PDE. So since I haven't really talked about any special methods, what we're actually going to do is we're going to use Fourier transforms and Laplace transforms in order to solve this PDE, because we already know some of the important properties of Fourier and Laplace. So let's see if we can get the solution for this. So the first thing that I want to take care of is that time derivative. So in order to do that, keep in mind, what is the strategy? We're going to be using Fourier transforms for taking care of x, and we're going to be using Laplace transforms for taking care of t. So you can go in any order, but I'm going to start with the Fourier transform. So I'm going to begin by taking the Fourier transform of the partial derivative of u, which currently is a function of x and t, and then I'm going to factor out that alpha because Fouriers are linear operators, so we're going to have alpha times the Fourier transform of uxx of xt. Right? Now I'm going to use those properties of Fourier transforms that we talked about last time. So the Fourier transform of a partial derivative of u of t is the same as the partial derivative of the Fourier transform with respect to time, which I'm just going to note as u hat t. And keep in mind now x is transformed into a new variable, let's call it psi of t. And over here we're going to have that's going to be equal to alpha. And the Fourier transform of the double derivative with respect to x is going to be equal to I psi squared times the Fourier transform of u, which is going to be u psi of t. So keep in mind I is just equal to -1, so that means I squared will be equal to, or I is the square root of -1, so I squared is equal to -1. So we can rewrite this as just u hat t of psi of t is equal to minus alpha psi squared times u hat of psi of t. Now that we have this, what I can do is I can rewrite this as the partial derivative of, let's say, u hat with respect to t is equal to minus alpha psi squared times u hat. And what I want to do is I want to take the Laplace transform of both sides of this equation. So I'm going to have the Laplace transform of partial u hat partial t, and that's going to be equal to minus alpha psi squared times the Laplace transform of u hat. Right? Keep in mind, Laplace is going to be focused on the temporal part, so that means psi is a constant as far as time is concerned. So what is the derivative, Laplace transform of a derivative? So we know that's just going to be equal to omega times the Laplace transform of u hat, right, minus the initial condition of the Fourier transform, right, because this is the Laplace transform of u hat derivative, not u derivative, right? So it's the initial condition of the Fourier transform, not the initial condition of u. So make sure you not to make that mistake. And over here we just have minus alpha psi squared times the Laplace transform of u hat. So what I want to do is I want to isolate my Laplace u hats to the same exact side. And what is that going to give us? So it's going to give us omega plus alpha psi squared times the Laplace transform of u hat will be equal to the Laplace, or the Fourier transform, of the initial condition function. Right? So what exactly do we have here? So I can solve both sides for the Laplace transform of u hat. So the Laplace transform of the Fourier transform of u will be equal to the Fourier transform of the initial condition of our solution divided by omega plus alpha psi squared. Right? So once we have this, then we can take the inverse Laplace transform of both sides of this. So we have that u hat will be equal to the inverse Laplace transform of u hat 0 all over omega plus alpha psi squared. Right? Keep in mind the variable in this case is going to be omega, and this is going to be a function of psi, not a function of omega, right? Because it's when t is equal to 0, right? And if t is equal to 0, that means the transform version of t is also constant. So once I have this, what am I going to have? So whose function is this? Well, that's just an exponential. So what we have here is u hat psi of t will be equal to u hat 0 times e to the minus alpha psi squared of t. Right? So that's the Fourier transform of our solution, right? So now let's talk about this character. So keep in mind ux0 was equal to u0 for minus 1/2 less than or equal to x less than or equal to 1/2 and 0 otherwise. So what exactly is this? So if we look at this graph, what we have here is from minus 1/2 to 1/2, we have practically a rectangular function, right? So that's just the scaled version u0 of the rectangular function of x. And we know the Fourier transform of that. So if that's the case, our solution can actually be rewritten as u hat times psi of t will be equal to the Fourier transform of u0 times the rectangular function of x times e to the minus alpha side square of t. Right? So what's the Fourier transform of a scalar multiple of the rectangular function? Well, that's just a scalar multiple of the complementary sinc function evaluated at pi psi e to the minus alpha psi squared of t. So that's u hat psi of t. Now all we have to do is take the inverse Fourier transform of both sides, and that's going to be our solution. So what is that going to give us? So that means u of xt will be equal to, so what is the inverse Fourier transform of this? So that's going to be equal to the integral from minus infinity to infinity of this function u0 or u0 of sinc of pi psi e to the minus alpha psi squared of t, and then times our e to the 2 pi I, positive 2 pi I, and then we're going to have psi of x d psi. Right? And that would be the integral representation for the solution to your heat equation with that prescribed rectangular initial condition and no what we call boundary conditions imposed on this particular problem. Right? So that's actually pretty nice. And you might be thinking, okay, well, am I going to carry out that integral? Actually, no. depending on that initial condition that I have chosen, it's a lot of the times not an elementary function that you can actually write this integral as. I'm not claiming that you can't write this one as an elementary function, but most of the time with PDEs, numerical methods are usually needed to write the analytical or approximate the analytical solution for that particular PDE. Right, so that's why numerical methods such an important field when you plan to explore this field in depth. Right? But that is some of the fundamentals that you definitely should know before diving into partial differential equations in a lot more detail. But there are so many more beautiful things that I want to share with you about PDEs, but we'll save them until a later video. So I hope you enjoyed this video, and I'll see you in the next one. Take care.